This is video 7 in our series of circuit analysis videos, and this is part 2 of mesh analysis. Mesh analysis part 2. So if you did not understand the previous video, mesh analysis part 1, go ahead and go back to that video. You do not want to start this video until you understand that one. So here's a circuit that I want to analyze. So I want to find essentially the currents everywhere. So the currents in every branch, the voltages across each component, and then I'm going to also find the power supplied or absorbed by each component. Okay, now if you remember in the previous video, we looked at mesh analysis, and we had a series of steps to perform mesh analysis. But the caveat to that was that our circuits could not contain current sources. So now this is part 2, and you'll see that this example here does in fact have a current source on the rightmost branch of 5 amps. So we're going to modify the procedure just a little bit. But if you remember, step 1, we're going to identify the meshes, okay, and pick a direction, clockwise or counterclockwise, and label the mesh currents. Okay, and the mesh currents are what serves as our unknowns. So there's mesh 1. Right? A mesh is a loop that contains no other loops. So here's mesh 1, and I'm going to choose the direction clockwise and label that I1. Now here's the second mesh over here. Alright, this is mesh 2, and I'm going to choose the direction counterclockwise to go with the current source. Right? You don't have to do that. You can pick whichever direction you like. Right? Hopefully by this point in the series of videos you understand that the directions don't matter. That you get the right answer. Hopefully, you get the same answer regardless of which directions you pick. Okay, the same conclusion. You just get a minus sign. So, but just to kind of make the calculations just a little bit simpler, I'm going to pick the direction that goes with the 5 amp source. So I'm going to call I2 this hypothetical mesh current that goes counterclockwise in this mesh. So it aligns with the 5 amps over here. Now, we said that, okay, if there are n meshes, there are n unknowns. So here's one mesh, 2 meshes. There are 2 meshes here. There are 2 unknowns, I1 and I2. However, this is where the modification now happens. Here, I2, in this branch with the 5 amps, I2 is the only mesh current that is contributing to those 5 amps. In other words, mesh 1 is over here. Mesh 1 current is over here. It does not affect this 5 amp source. So in this branch, the rightmost branch, all we have is I2, and we have 5 amps. So that must mean then, and because our I2 aligns with the 5 amp source, same direction, that must mean that I2 is 5 amps. Hooray! You see, the current sources provide us information regarding our unknowns, just in the same way that the voltage sources provided us information in nodal analysis. The current sources let us know, oh, hey, in this example, I2 is 5 amps. So I2 is not an unknown, and the only unknown here is I1. So right away we see a modification. If we have nm meshes, okay, that's the number of meshes, then the number of equations we're going to need, that we're going to need, and the number of unknowns, right? Because we have to have the same number of unknowns as we do equations, is equal to the number of meshes minus the number of current sources. That's the modification here. So we have two meshes, right, and one current source, so we need one equation. Well, where do we get that equation? And it's going to be around mesh 1, because I1 is the unknown. So let's do KVL around mesh 1. Okay, and as always, I'll start at the top left of the mesh and work my way in the direction that I've chosen for I1. That is to say, I'll go clockwise. So the first thing I get to is the 4 ohm resistor. So I want to know what's the drop in the clockwise direction. So the drop is, well, from Ohm's law, I1, right, times 4 ohms, I times R. So the drop is I1 times 4 ohms. Okay, that brings me here to this node up top, this T-shaped node, and I'm going to come down through the shared branch. And again, in the direction of the current, I want to know what is that drop across the 6 ohm resistor. Well, again, from Ohm's law, I've got the current, I1 is with me, okay, but I2 is affecting that current, and I2 is also with me, plus I2, but we know what I2 is, it's not unknown, it's 5 amps. Okay, then times the 6 ohm resistor. So that puts us at this bottom node down here, and I need to get back to where I started, which is the top left of the circuit. So I'm going to traverse this 10 volt source, and that's an increase, notice the polarity, of 10 volts. So because I added all the drops, when I get to an increase I have to subtract it. Okay, and I'm back to where I started, and so all of that is equal to 0. It's KVL. Okay, there's my one equation, right, and one unknown. So I can solve that. So I've got 6 ohms times I1 and 4 ohms times I1. That makes 10 ohms times I1. And I've got 5 amps times 6 ohms. That makes 30 volts minus 10 volts. And when I get that to the other side, I've got minus 20 volts. Okay, so if I solve for I1, we see that I1 is minus 20 volts over 10 ohms, or minus 2 amps. Okay, and we have it. So this circuit, using mesh analysis, took one equation and one unknown. If we use nodal analysis, if you'll recall, we have 1, 2, 3, 4 nodes, minus 1 for ground, minus 1 voltage source. Nodal analysis would have taken 2 equations here. So mesh analysis is the way to go. So we've got minus 2 amps. So what that means is the current, don't be afraid of the minus sign, that just means we chose the wrong direction. The current is actually going, let me use lavender, counterclockwise. So this current in this branch now, so this is a real current, meaning it's a branch current. This current, lowercase I1, is equal to 2 amps going that way, right? And we already know that this branch current here, only I2 contributes to that current. So that's 5 amps from this source. 5 amps is bringing current up this way, so the 5 amps comes over here. Okay, so out of that 5 amps, 2 amps comes this way. And so how much goes this way? Well, 3 amps, right, from KCL. But we can also see that that current, that shared branch we said was I1 plus I2, because that arrow is going in the same direction as I1 and I2. So I1 is minus 2, I2 is 5, so I1 plus I2 is 3 amps. So it checks out. So we've got all of the branch currents. That's good. So let's get the voltages next. So the voltage drop across this resistor, let me erase the polarity. So if I want the voltage drop across the 4 ohm resistor, I know 2 amps goes through it from right to left though. So let me indicate that with the plus minus. And you know that the voltage across a resistor always goes from high potential to low, or the current through a resistor goes from high potential to low potential. That is, the marble always rolls down the ramp. Okay, so we know that the right is going to be the higher potential, the left is going to be the lower potential. What is that voltage? Well, we've got 2 amps and we've got 4 ohms. So Ohm's law says that that is 8 volts across. Alright, similarly, with the 3 ohm resistor, we know that 5 amps are traveling through it from right to left. So we know the voltage drop across that 3 ohm is right to left. And how much voltage? Well, we've got 5 amps through 3 ohms. So 5 amps times 3 ohms gives us 15 volts. 15 volt drop. Now the drop across the 6 ohm resistor, we see that current is going from top to bottom. So the drop must also be from top to bottom. And we have 6 ohms and 3 amps, so that's 18 volt drop there. Alright, so we know the voltage across almost every component. So what's the voltage across the 5 amp source? That's the only component whose voltage we don't know yet. Well, the 5 amp source is connected from this node. Let me use a lighter blue. Right, the 5 amp source is connected down here and connected to this node up here. So what's the voltage drop across those 2 nodes? Well, if we call this 0 volts down here, that's maybe our reference. Okay, well, we know that from here, this T node, to here was a drop of 18. So if this is what we're calling our reference to be 0, then that makes this 18. And then we know that there's an increase of 15 to get to over here. So if we had an increase of 18 and then an increase of 15, well, from here to here then is an increase of 33 volts. Right? So what's the voltage across the current source? Well, if this is 0 and this is 33, then the voltage drop is 33 volts. So now we're ready to find the power in each component. Let's do that. So the power in the 10 volt source is the voltage across it, which is of course 10 volts, times the current through it. The current through it is 2 amps. So that is 20 watts. 20 watts of power. And notice here that the current is entering the positive side and leaving the negative side, just like in a resistor. So this 10 volt source is absorbing power. So we'll make that plus 20 watts. Absorbing power. Yes, sources may absorb power. You charge your batteries, for example. Alright, let's find the power in the 4 ohm resistor. So we've already said that there are 8 volts across it and 2 amps through it. So that is 16 watts of power. And of course, current goes from high potential to low potential in a resistor, so that is absorbing, so positive. The power in the 6 ohm resistor, we've already said that there are 18 volts across it and 3 amps through it. So that is what, 54 watts. And again, a resistor is always absorbing power. Okay, the 3 ohm resistor, 15 volts across it, 5 amps through it. That would be 75 watts of power that it's absorbing. Now, how about the current source? The power in the current source. Well, there are 5 amps through it, 33 volts across it. So 33 volts, 5 amps through it. And so that is, what, 165, I think? Alright, and notice here the current is going from low potential to high potential. So that's the marble going up the ramp. So that's an active, so meaning it's supplying power. So that's negative. And if we take all of those guys and we sum them, okay, we should get, and we do, we get 0. That is to say, this is a closed circuit, right? All of the power that's being supplied is absorbed by the other components. Okay, that's mesh analysis with a current source. Let's look at another example. Right, so suppose we have 20 volts here. Right, and we have 6 ohms and 2 ohms. And then we have, let's say, a current source here of 6 amps. Alright, so here we go. And over here we have a 10 ohm resistor and a 4 ohm resistor. Okay, so yes, you could combine the 10 ohm resistor and the 4 ohm resistor, because they are in series, but we're just going to leave them be for right now and just work on our mesh analysis skills. So you see that this is kind of the same topology as the previous example. That is to say, there's a mesh on the left and a mesh on the right. Okay, so we'll call this mesh 1 over here and mesh 2 over here. Now, I'm going to choose my direction for mesh 1 to go with the current source. So I'm going to go counterclockwise. There, we'll call that I1. Okay, counterclockwise. I'm going to choose clockwise for mesh 2. Now, if you didn't do that, if you didn't align your currents to go with the 6 amp source, again, that's fine. You'll get the same answer. You'll get the correct answer. Either way, it doesn't matter. It just circumvents a negative sign that we'll need later. So we're just going to pick our currents to go with that current source. Now, a question you might be having at this point is, which one of these is going to be our unknown? Remember, the number of equations that we need was the number of meshes minus the number of current sources. So there are 2 meshes and there is 1 current source. So for this example, we need 1 equation and 1 unknown. So is our unknown going to be I1 or is it going to be I2? And which mesh do we use to perform KVL? Right? Well, let me show you a problem that we're going to have with either mesh. So for example, let's do mesh 1, and I'm going to write this in red because you're going to see a problem. We're going to erase this in a second. So if I started at the top left and I found the drop across the 6 ohm resistor, that would be I1 times 6 ohms. Right? And then if we went through the 2 ohm resistor, the drop across it would be if we're going, excuse me, we would go in the direction of I1. So let me back up. So if we started top left, and I'm going in the direction that I've chosen for I1, we're going to go this way. So we drop by 20 volts. Okay, that puts us down here. Now, I need to traverse this thing, the current source. Okay, but what's the voltage across a current source? What's the drop here? Well, for voltage sources, it's obvious, 20 volts in this case. For resistors, I can use Ohm's law. But what about current sources? Well, if you understood nodal analysis, here we have the same issue, or similar issue, that we can't write an expression for the voltage across a current source. Okay, so we're in trouble if we try to go up this branch. So what we're going to do is, let me erase that, we're going to combine the two meshes into one. And I'll show that in purple here. We're going to go this way. Okay, we're going to combine the two meshes into one mesh. And this thing is called a supermesh. And let's be concrete here. A supermesh forms when two meshes share a current source. Okay, so this is the new idea now, right? This is why we broke mesh analysis into two pieces. So I've got mesh 1, right? I've got mesh 2, and I can't go through this branch. So I'm going to combine them. They share that current source. So I'm going to combine them and make a supermesh. And doing KVL around the supermesh, that's going to give me my one equation. Now the question still is it going to be in terms of I1 or I2? Well, either one is fine. So at this point, we should see a relationship between I1 and I2. They both contribute to the 6 amps. And they both are in that direction. So I1 plus I2, right, is the current in that middle branch, which is 6 amps. So we know the relationship between I1 and I2, so let's just pick one to solve for, right? Let's pick I2 is 6 amps minus I1. Okay, and now when we set up our KVL equation around the supermesh, whenever I would use I2, I'm going to instead write 6 amps minus I1, and so I'll have one equation that's in terms of only I1. And so I'll have one equation, one unknown, and I can solve that equation. Alright, so the direction, again, is not terribly important, but I'll start at the top left, and I'll go in the direction of I1. So we'll do KVL around the supermesh. Okay, so I first have a drop of 20 volts. Notice the polarity. That puts me down here, and I'm going to go with the purple, so I'm going around the supermesh. So the next thing I have is here, the 4 ohm resistor, and I want the drop in this direction because that's the way I'm going. So the drop in that direction, well, I've chosen I2 to be down, but we know that the drop in the direction goes with the current. So the drop is minus I2 times 4 ohms, right? Because I2 we've chosen to go down, and I want the drop going up. And again, when I write I2, instead I should use 6 amps minus I1. So I'm going to erase this, and I'm going to use 6 amps minus I1, okay, and then times the 4 ohms. Now, the only way to get good at this is to practice. So you've got to be doing the homework and see this stuff for yourselves. You can watch me do this a million times, but until you do it yourself, you're not going to have a firm grasp on it. Okay, so now we're up here, and we need the drop across the 10 ohm resistor. Right, again, I2 is opposing me, so I need a minus I2. Right, so that's minus 6 amps minus I1 times the 10 ohms. Right, that puts me here, and I got to get back to where I started. So now I need the drop from right to left. Oops, wrong color. From right to left across that 6 ohm resistor. So I1 now is the only thing that's contributing to that. And I1 is in that direction of the drop. So this is going to be plus I1 times 6 ohms. And I'm back to where I started then, up here at the top left. And so all of this equals 0. Alright, so we've got one unknown, I1, right? So I can combine I1s. Here I have when I distribute that minus, and I've got 4 I1, and I've got 10 I1, so that's 14, and then a 6. So that's 20 ohms times I1. And the constants here, I have a minus 24 and a plus 20, so that makes a minus 4. Then I have a minus 60. So minus 4 and a minus 60. That makes minus 64 volts equals 0. Okay, so we can easily solve that. Let's do it. I1 equals, we'll add the 64 volts to the other side, divide by 20 ohms. Alright, and there is, what, a 4 there. So this is 116 volts over 5 ohms, which is 3.2 amps. 3.2 amps. Alright, so that's I1, and remember the relationship between I1 and I2 was here. So that makes I2 to be 6 amps minus 3.2 amps, which gives us 2.8 amps. Alright, so now those were the hypothetical currents. Now let's talk about the actual branch currents. The current here in this branch, okay, is with I1, and only I1 contributes to it. So this is 3.2 amps in this branch. Similarly, in this branch, at the right, I'll draw the arrow here. I'll draw it with I2. Okay, only I2 is contributing to this branch current. And so this current is 2.8 amps. Okay, and notice here we've got 3.2 amps coming in, 2.8 amps coming in, then they add to the 6 amps. This current in the middle shared branch is, of course, 6 amps. Alright, so we have the currents everywhere in the circuit. Now let's get the voltages everywhere across each component. So across the 6 ohm resistor, well, we have 3.2 amps going through 6 ohms. Okay, so the voltage across this resistor is the multiplication of that. So that's 19.2, I believe. 19.2 volts here. 19.2 volts. 6 ohms times 3.2 amps. And the drop is in the direction from right to left. It's in the direction of the current. Has to be. Alright, so we've got 19.2 volts across that resistor. We have 20 volts across the voltage source. Let's find the drop across this resistor here, the 10 ohms. I've got 2.8 amps going from left to right through the 10 ohms. So the drop is also from left to right. So I've got 10 ohms times 2.8 amps. That's 28 volts drop from left to right. Okay, similarly, I've got 2.8 amps through the 4 ohm resistor, and it's going from top to bottom, so the drop is also from top to bottom. 4 times 2.8, okay, is 15.2 volts. Alright, so the voltage across this resistor, well, I've got 6 amps through it, and the 6 amps are going from bottom to top, so the drop is also going to be bottom to top. 6 amps times 2 ohms, that's 12 volts. Okay, and now the drop across this thing, right? How do we get that? There's no formula to get the voltage across a current source. So let's call this guy ground for our reference. Call it 0 volts down here. Okay, notice if I call that 0, then up here is 20. This node is 20 volts. Then I increase by 19.2 volts. So up here is 39.2 volts in this T-shaped node. Then I increase by 12. So this voltage here between the current source and the 2 ohm resistor is 12 higher than 39.2. So that's 51, right? 51.2 volts. So the voltage across the current source, okay, we can remove the question marks now. Okay, the voltage across the current source from here to here is 51.2 volts. Good. And if we wanted to, then we could find the power in each component, but we won't do that. We just want to keep practicing our mesh analysis. Okay, so we're going to move on to another example. All right. So let's start with our current source. Okay, we'll say that guy is 5 amps. 5 amps. And we'll put a 2 ohm resistor up here. And a 4 ohm resistor. And a 2 ohm. 8 ohms here. A 10 volt source here. And maybe a dependent current source right there. Okay, so we've got labels there. Let's make the dependent current source 3I0, and we'll call I0 to be this current here, I0. Okay, so the current here is 3 times whatever the current here is. Okay, so there's our circuit. No, let's not make this 6. We'll make this 6 ohms. 6 ohms. Okay, and I do want to point out, in this circuit, we have no series resistors, we have no parallel resistors, so we can't use voltage division or current division, we can't combine resistors, anything like that, okay? So, you know, we have to go to our last resort, which is either mesh analysis or nodal analysis, and we're going to use mesh analysis in this case. Because, if you notice, we've got 1, 2, 3, 4 meshes. Okay, but how many current sources do we have? Well, we have the dependent one and we have the independent one. So minus 2 current sources equals 2 equations. Okay, so all we need are 2 equations here. If we used nodal analysis, well, let's count the nodes. We've got 1, 2, 3, 4, 5 nodes, minus 1 for ground, 4, and 1 voltage source, so that would leave us 3 equations. So nodal analysis would require 3 equations and 3 unknowns. Here we only have 2 equations and 2 unknowns. So nodal analysis is mesh analysis is the right choice here. Now, remember that a supermesh is a mesh, is when 2 meshes share a current source. Okay, so if we called this mesh 1, okay, and I1, and this mesh 2 and I2, those 2 meshes share this current source of 5 amps. So right away we see that I1 plus I2 equals 5 amps. Right? So we see the relationship between those two. Further, this mesh current, I3, is shared with I2, and so we see the relationship with those two. I2 plus I3 equals 3I0. Well, what is I0? Well, that makes this, we'll call this current I4. Mesh current I4, and I4 is the only thing contributing to I0, so this is 3I4. Okay, so I4, unknowns. I4 is going to be an unknown because it's in this mesh with itself, right? We're not going to combine it with any other meshes to make a super mesh. So I4 is an unknown. So at that point, right, we need to decide what is our other unknown going to be. Is it going to be I1? Is it going to be I2? Or is it going to be I3? Okay, we can only pick one other one. And I think the choice here should be I2 because it appears in both of these relationships. In other words, we know how I2 is related to I3. We know how I2 is related to I1. So let's make I2, the one that's shared between these two, let's make I2 the other unknown. Okay, so from these two guys, we have I1 is 5 amps minus I2, Right? So if we knew I2, we could get I1. And if we knew I2, we could get I3. Okay, here's our relationships from the current sources. The current sources give us information regarding our unknowns. Alright, so we kind of have a super mesh. Meshes I1 and I2 combine to make this super mesh because they share the 5 amp source. But meshes I3 and I2 also share this current source, so that gets kind of combined, and we have this super mesh. Okay, and so we're going to do KVL around the super mesh, and whenever we need I1, we're not going to write I1, we're going to write 5 minus I2. And whenever we need I3, we're not going to write I3, we're going to write 3I4 minus I2. Then we're going to do KVL around mesh 4, and that's going to involve I4 as well. So we're going to finish with 2 equations using only these 2 unknowns. Alright, let's do it. KVL around the super mesh. Super mesh. Okay, so I'll start at the top left and I'll work my way, and we'll go counterclockwise to go with kind of I1. So if I'm following the purple dashed line. So I start here, coming down here. So the drop in the direction that I'm traveling, right? Traveling this direction, is, well, it's I2 is the only mesh current in that resistor. Okay, but I2 I've chosen the other way, not from top to bottom, but from bottom to top. So I need a minus I2, and I2, I'm not going to, I2 is one of my unknowns, so that's okay. I2 minus I2 times 6 ohms. That's the drop from top to bottom. So that puts me down here. I'm going with the dashed line. So the next thing I hit is the 8 ohm resistor. So I need the drop in this direction, from bottom to top. So both, so I'm going with I3 at that point. With I3, because I3 is circling around this way. So I'm going with I3, and I4 is opposing me. So I'm going to write plus. I3, I'm not going to write. Instead, I'm going to write 3I4 minus I2. And then I4 opposes me, so minus I4. Remember, these are our unknowns that we agreed upon at the beginning of this, so I can only use these guys. So there's the current through 8 ohms times the 8 ohms. Gives me the voltage drop from bottom to top. So that puts me up here. I'm going with the purple dashed line. So the next thing I have is the 4 ohm resistor. So the current through that is just I3. And I'm not going to write I3, I'm going to write this thing. 3I4 minus I2. Then times the 4 ohms gives me the voltage drop. That puts me here. Last, I have the 2 ohm resistor that's in the direction of I1. The drop is in the direction of I1. Okay, so that's plus I1 times 2 ohms. But I'm not going to write I1. I'm going to use 5 amps minus I2 times the 2 ohms. And I'm back to where I started, so that all equals 0. Alright, so I've got for I2 I've got a minus 6, a minus 8, so that's minus 14, and a minus 4, that's minus 18, and a minus 2, that's minus 20. Minus 20 ohms times I2. For I4, I've got 24, and I've got, I guess inside the parentheses here I have 3 minus 1, so 2 times 8, so that's 16, I4. 16 and a 12. 16 and 12 is 28. 28, and that's it. So I've got a plus 28 ohms I4. Now for the constants, I only have this guy, the 2 ohms times the 5 amps. That makes 10 volts. When I subtract it over, that makes minus 10 volts. Now if you like here, you can divide by 2. So this would make minus 10 ohms times I2 plus 14 ohms times I4 equals minus 5 volts. Alright, so we'll put some stars by that and call that equation 1, and we'll come back to it. Now, I've got one equation there and 2 unknowns, so I need another equation, and mesh 4 is going to give me that equation. So let's do KVL around mesh 4. Okay, so I'll start at the top left, and I'll go in the direction of the current that I've chosen. So let me erase this polarity here. So now I want to know, what is the drop across from top to bottom, the 8 ohm resistor. So I4 is going with me. I3 opposes me, so minus I3, but I'm going to write this instead. Minus 3I4 minus I2. That's the current in the branch times the 8 ohms. That's the drop. That puts me down here. Now I need to increase by 10 volts, so that's a minus 10 volts. That puts me at the top right. And I need the drop in this direction from right to left. And the drop across that thing. Only I4 contributes to that current, and that's in the direction from right to left, so that's plus I4 times the 2 ohms, and I'm back to where I started, so that gives me 0. So let me combine some like terms here. Let me work on these double parentheses. I've got I4 minus 3I4, so that makes minus 2I4, and then a plus I2 times 8 ohms plus I4 times 2 ohms, and I'll get the 10 volts to the other side. Now I've got a 8 ohms I2. I'll put it in the same form as equation 1. So I've got 8 ohms I2, and then I've got minus 2 and plus 2. That's nice. Excuse me. The minus 2 times the 8 gives me minus 16, plus 2 is minus 14. So minus 14 ohms I4 equals 10 volts. If you like, you can divide by 2 here. 4 ohms I2 minus 7 ohms I4 equals 5 volts. Let's put some stars there, and that's equation 2. Alright, so we need to solve this system of equations. We have 2 equations, 2 unknowns. Solve that any way you like. I'm just going to put it in reduced row echelon form. So I'm going to put this in a matrix. I've got minus 10, 14, minus 5, 4, minus 7, 5, and let's get that into reduced row echelon form. So, matrix dimension, I've got 2 rows, 3 columns. Alright, so the first row, negative 10, 14, negative 5. Negative 10, 14, negative 5. Second row, 4, negative 7, 5. 4, negative 7, 5. And we'll say solve. And our solution is there. Okay. So our solution after the reduced row echelon form is I remember that this row, or excuse me, this column was I2 and this column was I4, and this was the constant. So our solution is I2 is equal to negative 5 halves amps, and I4 is equal to negative 15 over 7 amps. Okay, now I want to do one more example. Okay, so I'm not going to find the voltages and the powers and so forth, but I just want to point out what you would do next to solve this guy. So now we have our unknowns, I2 and I4. With those, we can get I1, right? 5 minus I2, and we have I2. And we can get I3, 3 times I4 minus I2. So we have all of the mesh currents at that point. So we can get the branch currents, as we have been doing, and then we can get the voltages across the resistors, and then finally the powers in each component. Okay, let's do one more, and then call it a day. All right. So we've got 8 volts there, 2 ohms, and a current source here of 4 amps. 1 ohm, four ohms, 2 ohms, and 8 ohms. Right, and we want to solve the circuit, so we want to know the voltages everywhere and the currents everywhere, and we're going to use mesh analysis to do so. Again, I want to point out that no pairs of resistors are in series with one another. No pairs are in parallel. So you can't combine anything here. You can't use voltage division, can't use current division. Our last line of defense is mesh analysis and nodal analysis. So we're going to use mesh analysis here. Alright, so let's call this current to be I1, this mesh current to be I2, and this mesh current to be I3. Alright, so you see, remember, I'll write it again, a supermesh is a mesh when 2 meshes share a current source. Okay, so which meshes here share a current source? Yeah, 1 and 3, right? So they're going to be combined into this thing. Okay, so there's our super mesh. So we're going to do KVL around that purple super mesh, and then we're going to do KVL around mesh 2 And those equations will give us our two unknowns when we solve them. Alright, let's do KVL around the Supermesh. Okay, so I'll start at the top left. I'll go in the direction of the current, which is I1. So the first thing I get is the 2 ohm resistor. And so the drop across that 2 ohm resistor in the direction I'm traveling, so from top to bottom, okay, is the current through it. So I1 is going with me. I2 opposes me. So I1 minus I2 times the 2 ohms. That gives me the drop there. So notice I'm using I1 as an unknown. That means we're not going to use I3 as an unknown. We know the relationship between them is I1 plus I3 equals 4 amps, excuse me, because they're in the same direction as the 4 amp source. So whenever I want to use I3, I'm going to use instead 4 amps minus I1. Alright, so now I'm here, and I need the drop across this 4 ohm resistor in that direction, from left to right. So I2 opposes me, and I3 opposes me. So it's going to be minus I2 plus I3. But I'm not going to write I3, I'm going to write 4 amps minus I1. Then times 4 ohms gives me the drop. Now the drop across the 8 ohm resistor from top to bottom. I3 opposes me, so I need minus I3, and I'm going to write 4 amps minus I1. And the voltage drop is when I multiply by the 8 ohms there. Using Ohm's law, I have the voltage drop. So that puts me down here. I'm going with the Supermesh, so that around the dotted line, and I increase by 8 volts, so that's minus 8 volts. And back to where I started, so that's all equal to 0. Alright, so my unknowns are I1 and I2. Let me get the I1s together. I've got 2, got minus 4, so that makes minus 2, and 8, so that's 6. 6 ohms times I1. Okay, for I2 I've got a minus 2, and I've got a minus 4, so that makes minus 6, minus 6 ohms I2. For the constant, I've got 4 amps times 4 ohms, that's 16, but the minus makes minus 16 volts. And I've got a minus 32, so that makes minus 48 volts. And then another minus 8, so that makes minus 56. So I'll bring it to the other side, it makes plus 56 volts. Alright, so at this point, I think there's a 2 here, so we can have 3 ohms I1 minus 3 ohms I2 equals, and then if I divide by 2, 28 volts. And we'll put some stars there so it pops. We'll need it again and call that equation 1. And now let's go KVL around mesh 2. So I'll start at the top left. I'll go in the direction of I2, which is to say clockwise. So the first thing I need is the drop from top to bottom of the 2 ohm resistor. So that's I2 times 2 ohms. Then I need the drop, and let me erase the polarity here, So now I'm going the other way. I need the drop across the 4 ohms going from right to left. So that drop, I2 is with me, I3 is also with me. So that's plus I2 plus I3, but instead of writing I3, I'm going to write 4 amps minus I1. Multiply that by the 4 ohms gives me the drop. Finally, I need the drop across the 2 ohm resistor going from bottom to top. So I2 goes with me, I1 opposes me, so this is plus I2 minus I1 times the 2 ohms gives me the drop back to where I started, so that's equal to 0. Now let me put it in the same form as equation 1. So the I1s, I've got a minus 4 and a minus 2. So this is a minus 6 ohm times I1. For the I2s, I have a 2 ohm and a 4 ohm, so that's 6, and another 2, so that's 8, plus 8 ohm I2. Alright, for the constant, I have a 4 amps times a 4 ohms, so that gives me 16 volts, and when I move it to the other side, that makes a minus 16 volts. And here there's a 2 I can divide by if I like. So volts. Okay, and it's in the same form as equation 1. Let's call that equation 2. So I need to solve these things. So I could use the same method we used previously, which is the RREF, but notice if I add them, what happens? If I add the 2 equations immediately, I1 drops out, right? So that's nice. And even nicer is I'll have a 1 I2. So let's just add the 2 equations. And so I have 1 ohm times I2 equals 20 volts. So that makes I2 20 volts over 1 ohm, 20 amps. That was quick. Right? That's nice. We like that. And if I want I1, I can plug I2 into any one of these 2 equations. Let's just use the top one. Okay. Equation 1. So I've got 3 ohms times I1 minus 3 ohms times 20 amps equals 28 volts. So I've got the 3 amps times the I1. This makes 60 volts added to the other side. That makes 88 volts. And so I1 is 88 thirds amps. So we'll just leave it like that. Again, so I've solved the system of equations. I've got mesh 2 current, I've got mesh 1 current. If I wanted mesh 3 current at this point, here's the relationship right here. So I can get I3 because I have I1 now. So now I have all 3 mesh currents. I can get the voltages, I can get the branch currents as I've demonstrated already in this video, and the power then would follow. Again, try working on these on your own, and make sure you're completing the homework assignments.